So we're going to start off with a short puzzle. Is it possible for an object to have a constant speed but still be accelerating? You know what? Just for giggles, I think again, we're going to vote. How high you hold your hand up is how sure you are of your answer. Who says, Mr. Dueck, yes, you can have a constant speed and be accelerating? Is that a vote? Davin's going out on. Okay, I got. Oh, swaying. 1, 2, 3, 4, 5. I got 6. Who said no? You can't. Why is the correct answer yes? How can you be traveling at a constant speed but still be accelerating? Well, first of all, we defined acceleration as a change in velocity. Velocity is a vector. It has both magnitude and what? So if you're going around a corner at a constant speed, but your direction is changing, is your velocity then changing? Yes. So is there an acceleration? Yes. So you can be accelerating while going at a constant speed by changing direction. That's going to be what we'll be dealing with a lot during this unit. We're going to have an object moving at a constant speed in a circle. An object moving at a constant speed in a circle, what we're going to call uniform circular motion. Its velocity is changing because its direction is changing, and because its velocity is changing, the object must be accelerating. That means the net force cannot be zero. That means forces can't be balanced. There's a whole bunch of dominoes that fall into place as soon as you have that realization. In fact, this is the most important fact to keep in mind about an object moving in a circle. The object is accelerating. Its velocity at one point would be in this direction. Its velocity later on would be at that direction. It's accelerating. The next question we want to ask is, okay, what's the direction of the acceleration? To figure that out, we perform a vector subtraction. We start out with VF equals VI plus AT, and we get the A by itself. A equals VF minus VI over T. Time is a scalar, so the acceleration is going to get its direction from those two. How do you subtract vectors? We don't. What do? Okay, we're going to add the opposite. By the way, technical comment, I'm soon going to show you the acceleration is not constant, so this is only true for a very small interval. But we can show the direction by going VF minus VI, because dividing by delta t won't change the vector direction. I've got a zoomed in picture here. Here's the initial velocity. Here's the final velocity. By the way, when you're moving in a circle, we say that you are traveling at right angles to the radius. When you're moving in a circle, your velocity is always going to be perpendicular to the radius. The fancy phrase for that, calculus students, is tangent to the radius. You're going at right angles to the radius. Okay, so if I zoom into this picture here, I guess V final is this way, V initial is this way. I'm going to zoom out now so that you can see the whole picture. I'm going to subtract final minus initial. Well, what I'm really going to do is I'm going to say I add the opposite. So I'm going to go VF plus the opposite of VI. Now, VF is this direction. VI is up, a little more up and left. What's the opposite of VI? So here's VF, here's negative VI, and we add them tip to tail. The resultant is that way. That's the direction of the acceleration. In other words, you're accelerating toward the center. And this is the key understanding. When you're moving in a circle, which way are you accelerating? Towards the center. When you're moving in a circle, which way are you accelerating? Everybody. When you draw a free body diagram, which way is the winning direction? Same answer. Everybody. Toward the center. Who's winning? Which direction? Toward the center. Has to be based on all of our Newton's laws stuff. If you're accelerating in that direction, that's got to be the winning direction. Which way will the longer arrow always be pointing? Toward the center. So we see that an object that's moving in a circle is accelerating towards the center of the circle, or accelerating inwards. A ball on a frictionless tabletop is rolled along a circular track as seen below in top view. So we're looking down and the ball is rolling along, rolling along. When it gets to here, which path will it take when it reaches the end of the track? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. Path A, due to the fact that the ball has some circular momentum, which is going to keep it moving in a circular path for a while after it leaves the track. Or path B, because there's no force from the track, the object's going to go at a straight line, steady speed. Or path C, because when the track is no longer supplying a force to the ball will fly outwards. Let's vote. Who says, I think it's path A, Mr. Dueck. It's going to keep moving in a circle. 6, 7, 8, 9, 10. No, it's going to be path B, Newton's first. 6, 7, 8, 9. No, it's going to be path C because I've been on rides that move in a circle and I always feel like I'm getting pushed outwards. So if you took, for example, on the merry-go-round or the Playland ride, the Music Express, if the seat vanishes, I go flying out. You're going path C? What did you vote initially? Okay. Right here, the ball would be traveling in that direction, yes? And it's just left the track. What are the forces acting on it? Get the obvious one. Which way? Gravity would be into the page because we're looking down at it. Is it sinking down into the page? So there'd be a normal force out of the page. Those would cancel out. What other forces are acting on it? Are there any other forces acting on it? Well, then it's got to be B. It's got to keep going in a straight line at a steady speed, right? In other words, if I was spinning, sorry for those of you on YouTube, if I spin this around my head really, really fast, and I have a pair of scissors, if I cut the rope right when the ball was here, the ball would go in a straight line and hit Angus. If I cut the rope when the ball is right here, when the string and ball is right here, the ball would go exactly that way. It would not fly out, and it would not magically keep curving on its own because there's no force pulling it around in a circle once the string is cut. That okay? Next page. Why is it that the acceleration is inwards when the push that you experience in a car seems to be outwards? So you've all been in a car and the car goes around a corner and you feel like you're getting pushed out. You are not. There is no force pushing you out. What's really happening is this. So here's a person in a car. The car wants to turn left. The person wants to keep going in a straight line at a steady speed. Newton's first. However, the car is accelerating inwards. You keep going in a straight line at a steady speed, the car will eventually apply a force on you to keep you in the car. But the force on you is inwards. It's just that you're not used to the door pushing on you, and so you think to yourself, oh, I must be getting pushed outwards. It's really more noticeable if you're the passenger, because as the car goes around a corner, you find yourself being pressed against the door. No. The door is pressing against you. Your body tried to keep going straight. Your body tried to keep going straight. If you're the driver, it's not quite as noticeable because you actually exert a force on your body through the steering wheel. You exert a force on your body through the steering wheel, and you actually don't notice it quite as much. You really notice it, though, when you're a passenger. In fact, if you talk to your grandfather, he may fess up to this. In the 1950s and 60s, there were no seatbelt laws, and most vehicles had bench seats. They did not have bucket seats. And so if you were a young teenage boy going out on a date with a girl, you would get some surfboard wax and you would wax down your bench seat so that it was slippery, reducing the coefficient of friction. And then you would drive like this and you would make a quick right turn and the girl would come sliding into your, oh, hi, honey. Did the girl come sliding into your arm? No, the girl kept going in a straight line. The car is what moved underneath them. Ask your grandfather, he might fess up. Okay. Oh, here we go. I have to pause this one because Google thinks it's a bad video. Going on this rant because many years of experience in a car or on amusement park rides have made you believe, oh, I'm accelerating outwards. Remember, I taught you last year, your body is a backwards accelerometer. Whichever way you feel like you're getting pushed, I'm telling you, it's the opposite way. If you feel like you're getting pushed outwards, you are accelerating inwards. In fact, you may hear the term centrifugal force with an F, and that refers to this apparent outwards push. In fact, there's machines called centrifuges which use this, in quotes, force. But it's not a force. It's not outwards. It's in a straight line tangent to the radius, and it's not a force, it's just inertia, your body wanting to keep going in a straight line at a steady speed. And the vector analysis that we did shows us that the acceleration, and therefore the net force, is inwards. If fighter pilots move too fast into a loop, they can sometimes become unconscious due to a lack of blood flow to the brain, and this is sometimes attributed to centrifugal force. No, what's really happening? So let's look at a picture here. Let's draw in, most of the blood is in the torso right there. And right now it's traveling in this direction. It wants to keep going in this direction. Okay, the pilot pulls up. You may hear people say, the blood got forced into my feet. No, your head got forced away from the blood. The blood wanted to keep going in a straight line, and so it ends up pooling down there. But it's not because it got forced down there. It actually wanted to keep going in a straight line. Your head was what got pushed away. And so fighter pilots have to do special training to deal with this. If you don't have the special training, it can be a little challenging. Put your pencils down, look up. So which way was that tourist accelerating? If they were moving in a circle, they were accelerating toward the center. The blood wanted to go in a straight line, and so his skull, his brain, was getting forced away from the blood. This is a true story. In World War II, during the Battle of Britain, there was a pilot, a British pilot named Douglas Bader, who crashed, and he lost both of his legs above the knee. But otherwise he was fine. So there was such a shortage of pilots, they just retrofitted a plane with longer pedals and they put him back up in the sky. And what he found was he could dive down and pull more G's than anyone else because he didn't have any legs for his blood to pool in. So he would let German fighter pilots get right behind him. He would dive down, and fighter pilots having big egos, the German fighter pilot, if he can do it, I can, would follow him down. Then Doug would pull up. The German pilot would try and pull up, would black out, and would crash into the ground. And in fact, the German pilots memorized his plane and his number. They would radio each other. Hey, don't follow him. He's doing something. We don't know what's going on, but he can do something we can't do. True story. So I've told you the directional portions of acceleration. How do we calculate it? The proof is a bit long. I'm just going to give you the punchline. I do circular acceleration as a letter A with a C. That's a terrible looking A, Mr. Dueck. A with a subscripted C, and it's V squared over R, where V is how fast you're moving around in a circle, and R is the radius. This is a scalar equation. There's no vector signs because the direction is towards the center, but towards the center depends where you are in the circle. If you're on that side of the circle, towards the center is this. If you're on this side of the circle, toward the center is that way. So it's a scalar equation. If you ask for a direction, toward the center. For an object that's moving in uniform or constant speed circular motion, we can come up with an equation for V. First of all, If there's no acceleration changing speed, if acceleration is only changing direction, then d equals vt plus a half at squared just becomes d equals vt. Okay, so get the v by itself, Noor. If we're talking a circle, the distance is the circumference, which is 2 pi r. And if we're talking once around, we call that the period, and the symbol is a capital letter T. This is where I'm a bad teacher because last year I used a capital T for tension. I really shouldn't. Capital T is reserved for periodicity, the period of something, how long it takes for something to go around once. So this is also a scalar equation. The circular speed is 2 pi r over the radius. This gives us a weird situation. I've taught you some habits in Physics 11 that you're going to have to unlearn if you're moving in a circle. Example 6 says this: an object is moving at 4 meters per second in uniform circular motion. It accelerates at 2 meters per second squared for 3 seconds. Daniela, what does A want me to find? VF is 4 meters per second. Mr. Dueck, how can that be? It's accelerating. Yes, yes, but it's moving in a uniform circular motion. This acceleration is not changing the speed, it's changing the direction. It's continually going at a constant speed. And so if I want to find the distance traveled, you're going to be tempted, don't write this down, look up, don't write this down, look up, don't write this down, look up. You're going to be tempted to go d equals vit plus a half at squared, because they gave me an a, but that a is not affecting the distance, it's affecting the direction. This distance is just going to be 4 times 3. It will have traveled 12 meters. So there's kind of got to be a warning or a trigger. We're moving in a circle. Okay, the rules have changed. Rules have changed. Okay. So here's a good summary picture. Your acceleration is towards the center, which, by the way, also means on this area, the circular force is going to be towards the center, because if that's which way you're accelerating, that's which way your net force is going to be. Your velocity is at right angles to the radius, and we say that the velocity is, quote, tangent to the radius. I guarantee there will be a multiple choice question asking you something about the direction of acceleration or velocity or force or some combination thereof. There's a second equation for circular acceleration. Because circular acceleration is v squared over r, but v is 2 pi r over the period, I can substitute this into the v. I'll get this. A equals over r, 2 pi r over the period, all squared. Well, really what that means is that squared is going to go onto the 2, onto the pi, onto the r, and onto that. So what I'm really going to get is A equals, what's 2 squared? What's pi squared? Pi squared. And then I have r squared over t squared, and there was already an r on the bottom from the original equation for a. Oh, there's an r squared on the top, there's an r squared on the bottom. These are your two equations for centripetal or circular acceleration: v squared over r and 4 pi squared r over t squared. Can you find where they both are on your blue sheet, please? Or on your yellow, on your formula sheet? Know where they are. I probably said AC equals V squared over R equals 4 pi squared R over T squared. How do I know which one to use? Oh, if the question gives me or mentions speed, I'll use the V squared over R. If the question gives me or asks for the period, I'll use the 4 pi squared R over T squared. It's not going to be, I was going to say it's not going to be rocket science. Next unit, it will actually be rocket science, but it's not too tough to figure out. So here's our summary. AC equals V squared over R, or it equals 4 pi squared R over T squared, where T is the period, how long to go around once. R is the radius of the circle, and V is 2 pi R over the period. And I think I gave you that one on your formula sheet as well, yes? No? Yes? Yeah, I used to not give it. I used to make kids just derive it. Alrighty. So I gotta be a little technical. In uniform circular motion, when we're moving in a circle and we're not speeding up or slowing down, we have a weird situation. The object is moving at a constant speed, but it is accelerating. How? The acceleration is changing the direction, not changing the speed. And the acceleration vector is changing in direction. You can see here it's pointing up and left, here it's pointing down and left, here it will be pointing down and right. The vector, the direction is constantly changing, which means this is technically a changing acceleration. That means we can't use our constant accelerations from physics 11. We can't use VF equals VI plus AT. We can't use D equals VIT plus a half AT squared. We can't use VF squared equals VI squared plus 2AD. Instead, we have to use our uniform circular motion equations. AC equals V squared over R, or 4 pi squared R over T squared. V equals 2 pi R over the period. And D equals VT, no plus a half AT squared. A little weird. Have to unlearn some habits. Next page. The Earth is currently rotating. Yes, it is, Mr. Dueck. Imagine that through some bizarre cosmic catastrophe, the Earth instantly stopped rotating. But those of us on the Earth's surface maintained our centripetal velocity. We would all go flying into a wall due to our inertia. First question, which wall of my classroom would we all go smashing into? North, south, east, or west? And convince me. I think there's two you can probably eliminate. Which two would you eliminate as directions? Okay, it's not going to be north or south. You can cross out the N, you can cross out the S. So the question is, right now, what direction are we moving? Are we moving east or are we moving west right now? By the way, west is that way, east is that way. So really what we're asking here is, are Noor and Matt going to get crushed by these people, or is Daniela going to get smooshed by these people? That's the question. Well, where does the sun rise? In the east. Is the sun really moving, though? So for the sun to appear to move from east to west, which way must the earth be moving? If it looks like the sun is moving in this direction, which direction must the earth be turning? Earth is moving that way. Earth is moving east. So I'm sorry, Daniela and Abby and Peter, you're the ones that are going to get squashed. It will be short, but we would all go flying into the east wall. The next obvious question is, if you're on the equator, how fast will you go smashing into a wall? Okay, that's a good question. What does this want us to find, Trevor? What path are people at the equator tracing out? Starts with letter C. So we're going to find centripetal or circular speed, which is 2 pi r over the period. This unit and next unit, you're often going to start to be using the back page of your formula sheet, which has a whole bunch of data, because on the back page of your formula sheet, they did tell us the radius of the Earth. What's the radius of the Earth? 6.38 times 10 to the 6th. What's the period of the Earth's rotation? It's also on the back. Sorry? Can't be 8.64. There's got to be there's got to be a times 10 to the with that. 8.64 seconds would be crazy. Well, you didn't read that. 8.64 times 10 to the 4th. Come on, you're all dying to know. How fast would people at the equator go smashing into the nearest eastern wall? Or if there was no wall, how fast would they go tumbling along until they hit something? Oh, 8.61. Why did you say 8.64? Oh, I'm sorry, I didn't hear. Thank you. Fix that. What do you get? Now, you might get an error. You all want to try this. Depending on your calculator, is this a fraction? Is there more than one thing on the top bracket? 2 times pi. You might need to put a times after the pi before the 6.38. Scientific notation button 6 divided by 8.61. Scientific notation button 4. I'm thinking 466 because I know how to round off because I passed grade 8. Yes? Units. Units. How many kilometers per hour is that? Could you multiply that by 3.6? How many kilometers per hour is that? Could you multiply that by 3.6? You're going to be hitting the, again, Daniela, the good news is your moment of pain will not last very long. Okay? No, this is Mach 1 is 343, so this is about Mach 1.2, but still fast. Was that a question or an answer? Hand up. Okay. So, where on Earth would your preferred location be if such a disaster were to occur? Where would you not notice anything? Where would you be fine? Trevor, North Pole or the? Now, we don't have a permanent settlement on the North Pole because it's on Arctic ice that moves. We do have a permanent settlement on the South Pole. So, yeah, your preferred location would be North or South Pole. In fact, if this did happen, the people on the South Pole, their only inkling that something had gone wrong would be when radio messages weren't getting returned. That's odd. What's going on here? Okay. Even if you were a few kilometers, even if like 100 kilometers from the South Pole, you almost certainly wouldn't notice much at all. Yeah. You got the wrong answer? Ah, you're going to need to find the pi button. Let me just hit pause for a second. Okay. Mr. Dueck will now mention a little bit about angular or circular momentum and show you some cool demonstrations as well as an addictive toy. Mr. Dueck forgot to get the addictive toys out, but he can get them out right now. Okay. Number one, this will be due Wednesday, or this will be due Thursday next week because your test is Tuesday. Number two, Number 3, take a look at number 4, please. It says, explain how the spin cycle on a washing machine works to partially dry clothes. You may have seen your washing machine during its spin cycle. The water is not flying straight out. The water is flying, 3 words, tangent to the radius. The water, if you take your phone and you video it in slow motion with the flash on, you'll see the water is traveling in that direction, not flying straight out. It's its own inertia going in a straight line at a steady speed. So I didn't assign 4. 5 is good. 7 is good. 8 is good. 9 is good. 10 is good, but tricky. 11 is good. 12 is good. 13 is good. There is 12 minutes left. Please use this, or you can play with the physics toys at the back. Let me pause the